Hello everyone, my name is Cheng. Welcome to the Dev Gym today. So today we'll be talking a little bit about the system design, right? So the agenda. So for today's talk, we got three parts. First part is I'll do a short lecture on what is system design, and after that we'll do a breakout session. This one we'll have three facilitators, where we'll have case study. So basically we have three groups, three sections of the room where we'll be doing deep dive into a case study scenario. So they will of how you would design a system, right? And we'll share a bit about the three systems that will be designed tonight later. And after that, once we have done with our thought process, we'll take a short break and come back and then do a share back. So each of the case study groups can do a share back of what they've learned, what the design they come up with. Yeah. And there's a QR code there for the slide, so you want to follow along. And actually, the case study is already in the slide. So you scan this, you can sneak peek into the thing already. So please do scan this, and you can access my slides. Yeah. Okay. Take 1 more second, 2 more seconds, 3 more seconds. Cool.
Or whoever has airdrop, I can post this ready for you. Airdrop.
Can. Yeah. Or you can just take a photo and.
Airdrop. Whoever
Okay. Check. Use the mic has given up on me. Okay, no worries. Okay, it's our battery. Oh well. Looks like I really do have a shower. No worries. Okay, so we'll just go straight in. Is my voice audible? Okay. Okay. Cool. So what is this system design, right? Let's go into that. So system design is basically the process of defining the architecture components, modules, and interfaces, and even data for a system to satisfy specific requirements. So basically, you're building all different parts of the like front end, back end, everything in between, where you can store the data, all the different components and modules that you need to build a software that will serve a purpose, right? So yeah, usually it's a critical aspect of software development. So we need to figure out what are the components you need to build, what are the components that your team need to build to serve the users to basically to perform a task, right? And this task usually will depending on the type of application you're building. You need to be scalable, high performing. You also need the code to be maintainable, right? So how you design your system has impact on all these things, right? There is a video you can go check out. It's you can also scan this to watch this video. I'm kind of okay. I'm not going to say I'm lazy, but I'm going to say there are a lot of great materials out there. So this is what I'm actually plagiarizing him and putting all this on. So this is the video of the YouTube video from Bye Go, which actually talks about this. So my slides are actually based off the content of the slide, and all thanks to Sharon who shared the link with me. So yeah, so you can check out this video later. I think he explains it much better than me. But what I'll try to do in this next few minutes is to basically share with you the essence of what.
Today we're diving deep into the cornerstone of system design.
Okay, right. So First of all, we talk about building scalable systems. Like, what is scalability? The first thing you want to talk about is scalability, right? So basically, it needs to handle an application you're building needs to handle increasing load by adding resources without compromising system stability. Basically, you want to add on more things in a way that's scaling up, scaling horizontally but at the same time, your application or system needs to continue to serve its purpose without breaking down, right? So you want to do it efficiently, you want to balance, also want to do it in a way to balance the costs, because usually adding servers and all that costs money. When you add more of this, you may end up with a bill shock. You get and there's one time I built a system and we were setting up SMS for password reset, and we got bill shock when we got like $11,000 for bill for SMS. It was the company paid for it, not me, so it's okay. But it's still, yeah. Yeah, I think the company can afford it, but still, when you're successful, it's a good problem. Anyway, yeah. So you also have to coordinate your overheads, because there's also some coordination overheads, because you have so many components that you need to add. You need to make sure all these components can work together, right? So there's sometimes when you scale up, you also need to figure out how all these little components can work together effectively. There's also a scaling curve, which I think the video will actually talk a bit more into. Yeah, so it's about response time versus demand, right? You want to, with a lot of traffic hitting your site, you want to make sure that your response time is actually reasonable, as in your request time, response time, and your application. Anyway, yeah. So yeah, and when you scale stuff, you also have something called scaling bottleneck, because sometimes we have when building our applications, there could be a situation where you have centralized components and they are the single source of failure and single point of failure, and it could be a bottleneck for your application as well. So sometimes you got to figure out so one of the ways that we can figure out how to scale systems better is to find out where our single choke points in our system, right? So that you figure out that your database is a single choke point where you have a lot of requests coming in, its response time is very slow. That could be then that's cascade across your system, right? So basically, figuring out where your scaling bottlenecks are is important as well. So there are ways to mitigate some of these centralized components and how to make it better. You can use things like replication, basically scaling it horizontally, or you can use caching. So basically, instead of like hitting it and keep calling your server or calling the database for the rest of for a data set, you can cache it locally or cache it somewhere that you can read quickly. So some strategies we use for caching will be using like the Redis cache, or maybe a file level caching, or in-memory caching, right? So you pull something and you like make a request to the database, get the data. I know I'm going to be reading this all the time, and it's not going to change very often. Therefore, I can store it locally in memory or in some file or some Redis cache or whatever, even mem cache or whatever. But there's also a trade-off there. So the trade-off there being that if the data keeps changing, if it changes very frequently, caching it may not be a good idea, because then your cache will be stale, right? So finding a good balance of all these things is important. Sometimes it's also a bottleneck because it's a high latency operation, like you're running a very complex SQL query. That takes out a lot of time. One of the ways that we can resolve this or figure this out, in most relational databases, there's a log called the slow query log, which can tell you can set a threshold. If a query takes more than 5 seconds to run, you can you end up as a alert inside the log file. And then you can use that to figure out, oh, okay, I'm running a query which takes up more than 5 seconds, right? So those are the ways that we can kind of like do some CSI on our application and see what's going on, right? But of course, at the end of the day, we also need to have all these logs put in place. So that itself is also a challenge. So when scaling something, there are some principles that we follow. One of the ways is, so the 3 ways that the video actually recommends is statelessness, loose coupling, and asynchronous processing. So 3 ways that we looked at. So statelessness, basically a server don't hold on to client specific data between requests. So basically so each API coming in, it is a new request to the server. So the server doesn't need to keep any memory or information about you, but it's actually the information comes from the request itself. It could be that my request will include some information that the server can then transact with. For example, one way that most applications use is one thing that most applications use is a JWT token. JWT token is like a token which includes some information that is about you as a user. So when you are able to decrypt it, there will be information about, say, the username and whatnot, and what resources you have access to. And with this, my application don't need to make a query to the database to find out more about you. So that is, in a sense, if you have requests coming in, they are stateless. It doesn't need the server to keep hold of some information about you, the better it is. Which means I don't need to make additional calls. I already have the information on hand from your request. In this case, also any server can handle the request. So it doesn't mean when I query, make this query or make this API call to server A, I can only talk with server A, right? Because in a high scale environment, you have probably a load balancer, and behind it is a couple of application servers. So you want to make sure that you don't get stuck to just one server, right? Of course, there are also some situations where you do want a kind of stickiness, but again, having stickiness means I always go back to the same server, and that server could get overloaded, right? That could be a problem as well. So you want to make sure any of your servers can handle the requests. And sometimes you also externalize the state into caching. So for example, my earlier example of a application server with many app server behind the load balancer, each of these servers can handle the request, but then they still need some form of information about you. So they can have a centralized cache somewhere where they can refer to, hey, look, this user is coming in, his username is ABC. What privileges does this guy have, right? So instead of like checking your JWT token, I can actually reach out to a cache server like Redis server, and it will actually have information that I can read very quickly. The difference between going to a caching service rather than a database is that probably you don't have to create a new connection, and probably the return and request response time will be much faster going through a cache server rather than SQL, right? Because some SQL servers, they have a limited collection pool. So usually, like as you're running through a SQL server or Oracle server, there's only a limited number of connections, right? That the database can take. You actually slam it with a lot of requests, you may drop connections, which is not a good thing, right? Whereas a caching server like Redis actually can handle a lot of load, right? So that's also quite nice. Okay, so the second principle we do is loose coupling. We design system components that can operate independently with minimal dependencies on each other. So basically, try to make your components be able to interact based on a contract rather than, I need you to have an active connection between them, right? So when you have well-defined interfaces or API for communication, you make it such that you define the agreement between the two services rather than, I need you to always do something or be present. So loose coupling might be a good thing. Right, so you can also scale individual components independently. So basically you have like a couple of servers behind, each of them microservices serving different things. If you know that one particular microservice is taking a lot of requests, more than the rest, you can actually increase the load, increase the capacity of the server, right, without affecting the whole of the system, right? So loose coupling. Asynchronous processing. Sometimes when we make calls, we have to wait for a response, right? So I make API call, I wait for the response. Sometimes the response takes a long time, and this waiting time actually has a cascading effect. Sometimes when you have I make a call to like say a checkout process, but the checkout process needs to check whether you're allowed to check out for this particular item. But basically, the server makes a few more calls behind the scenes, and each of them, if one of them is slow, it cascades to you having a very slow request at the end of the day, right? So what you want to do is, so try to figure out where all these bottlenecks are and try to, maybe you can, if it's possible, make them asynchronous. One of the things that we usually try to do is, at least for me, is email delivery. If I send out an email, I don't need to send out an email immediately. What I can do is I can queue this up. Like I make a request, I just check out on something. I don't need to send it immediately. I don't need to immediately send out email at that point in time. What I can do is I can send a request, or I can send something to a queue, and the queue will basically trigger the email delivery much later on, right? So sometimes you can see that, I finished checkout already, but I still haven't got the email about the successful payment or whatever, right? That's because that thing is being triggered and processing in the background somewhere, right? So basically, it's asynchronous processes, right? So this basically doing this way, you can mitigate tight coupling and basically avoid cascading failures in your complex systems. So basically, as I said, if I make one KPI call and it's waiting on others, if one stops going, you get a 404 or 500 error, right? Which is not a very nice thing to do. Whereas if you can make it such that, oh, is this critical for me to get a response now? No, it's not really, right? So things like, as I said, maybe it's not critical for me to see the response. It's like email. I really don't need email, or I don't need to know that the synchronization with the external system is done. I don't need to know this because all I need to know is I successfully make payment, for example, right? So, but the challenges here then becomes about error handling, debugging, because you have so many things going on happening asynchronously. So, for example, I have this system where my team built, which is we receive your application, and then at the end of the day, we'll synchronize it with a legacy system to tell them, hey, look, this application has come in. Could you start processing this application? Sometimes the application server on the legacy system goes down, so we're like stuck. This item is now stuck in our queue. Sometimes we won't know until we actually check the queue. Oh wait, our queue has things stuck in there, right? So one way that my team has kind of mitigated this is to have an alert. We set up an alert on the queue such that when using SQS, how many of you use Amazon AWS, right? So the AWS will set up a queue, a SQS queue. You can set up what they call a dead letter queue. Dead letter queue basically will if I try to send something to this queue, if the worker failed to do it 3 times, you will then send to a dead letter queue. So the dead letter queue is kind of like saying, I've tried my best to send it to process this message, but I have failed to do so. I'm now going you to a backup or another external queue, which is called dead letter queue. So we have set up an alert on this dead letter queue. The moment the dead letter queue, the count goes beyond 0, we will basically send an alert. So we get a Telegram alert every time that dead letter queue piles up. So we know that there might be something going on. Maybe the legacy system is having maintenance. So we're kind of like, okay, it's maintenance, so it's quite fine. Or if it's the legacy system is actually still up, so what do we do? Then my production support folks can go in and try to re-queue the thing or maybe figure out why was it failing, right? Maybe there was something specific about the application that we need to fix, or there's really a system error somewhere. So on the first day when we launched one of our applications, we had this issue with applications not going through. It turns out one of the validation of one of our fields was stopping our users from going to the next form. And because we have alerts, we're able to figure this out much earlier. So in my team, the yardstick is I have to know before my customers know there's a problem, right? So yeah, okay. Anyway, right. So some of the scaling strategies. So I talk about high scalability being vertical or horizontal. So 2 ways. Vertical scaling is quite straightforward, increasing capacity of your server. So many years ago, I know of a company. I guess I can talk about it. Tech in Asia. Have you heard of Tech in Asia? Tech in Asia is like it's a blog, and they got bought by SPH and whatever. So the early days when I first got to know about this company, the founder approached me and asked me whether I want to join the company. So I kind of like do a bit of sleuthing, checking out. So I found out that for a very long time, the application actually runs a WordPress instance, and it's just one server. The database and WordPress is all on one machine. It's like, how does it take all this load? Oh, right. It just increased the capacity of the server, adding more RAM, adding more disk space, using a bigger EC2 instance. Yeah, so that's vertical scaling, increasing the capacity of one machine so that you can do everything together, right? So you add more RAM, add more CPU, and especially in our cloud. Now that everything is on the cloud, you can easily just go in and click a button. Oh, I have 15 GPUs that control the thing. So yeah, benefits of the cloud. If you're on-prem, sucks to be you. But I'm going through this as well because of my team has to kind of move from on-prem to the cloud as well. So it's not trivial, I know. Anyway, so but there are also physical and economic limitations because, as I said, as I add more resources, I got to pay more, right? So the question is, can your company afford to pay that amount? Or can you have the budget to pay that amount, right? You don't have a situation where I send like $11,000 worth of SMS, then yeah, questions may be asked. So yeah, so question is, can you afford it? And well, of course, there's also physical limitations. There's only X number of GPU cores you can add, and before you can work. Okay, yeah. So can be very expensive if you really do scale this up. Horizontal scaling is a bit different. So it's instead of scaling up, you're scaling horizontally. You're scaling out. You're adding all machines to share the workload, right? So you have multiple servers or that can work in parallel. You can share the load. So one of the things that we know of or use are like database servers. So in some database servers, they have a concept of a primary cluster and secondary cluster. So basically, they have a bunch of servers that work in tandem together, and they all can serve requests coming in, right? So that's one way you can scale out, lah. But then again, there's also synchronization issue where all your machines in your read cluster has to be able to synchronize all the data effectively. If there's there's an issue with one of the machines that cannot sync up with the rest, then could have data problems or data corruption or data integrity issues. Yeah. So you can scale out. You can scale out, yes, but you have to be mindful of this kind of potential problems that could happen. So yeah, data consistency across machines, complexity of managing distributed systems. So like for example, caching, right? There was one time I actually had an application where we wanted each server to have its own cache, but for some reason one of the machines couldn't renew its cache properly. So it kept serving with stale data. I was like, oh shit. Yeah, so yeah, making sure that things work effectively is important. Yeah. So some concrete examples, like load balancing, which I talked about, you distribute the traffic across multiple machines. So like most of the time we use AWS, there's a concept called network application load balancer, ALB, or network load balancer. Usually once you set this up, there's the entry point for your application, and you can put many EC2 instance or EKS instance behind the scene. So basically, and all of this will basically you get all the traffic across it. And sometimes the different strategies for distributing load. There's a concept called round robin. Round robin, basically, I have a server A, B, C, D. I'll basically, as a request comes in, I'll send an A, then I'll send a B, send a C, send a D. So it's round robin. The last strategy is load based. So basically, you will basically check, the load balancer will actually check. So what's the CPU load? What's the CPU load? What's the CPU load? If particular server C is having high CPU load, I'll basically, the next request, I'll skip C. I'll go to the next one, right? So there's a couple of strategies you can do with this. So caching is another thing. So CDN caching is like, when we request for a GIF file or JPEG file, sometimes you don't actually get the file directly from the server. We get through a content delivery network. So the URL actually, they have a way of like, oh, you are physically in Singapore. I should then maybe when you hit this URL, the DNS will basically try to push you to retrieve the file from a Singapore-based edge server or CDN server. So having it distributed physically, there's some advantages. For example, you retrieve a file from US, right? It takes about 1 second. So I can remember. So there's a 1 second, right? So because of the speed of light, because fiber cables, the speed of light around the world, is about 1 second. It takes about 1 second to reach you. So yeah, if you have a file that's closer to you, you get the file faster. Because that's just shorter distance to travel in the fiber cable. So database sharding and a few others. Okay, right. So okay. So I've talked about technical things. When you talk about design system, we think about what are the technical components we need to throw in to scale up, scale down, scale horizontal, scale up, whatever. There's some other parts of this where is the non-functional requirements. This is not covered in the video. This is like bonus material for you. So non-functional requirements are basically non-technical things. What do we talk about? We will talk about when we think about different solutions, we also want to think about the trade-offs. What are we gaining? What are we losing in taking certain decisions? There are also other things there's also the question of complexity, which is basically if I add a new component or whatever, will it add more complexity to how much I have to control or manage and coordinate in my application? And thirdly is the team culture. Whether the team is able to accept some of these new developments. So yeah, so whichever solution you pick later on, or when you're doing a case study, kind of talk about the trade-off. What do we gain from using this solution? What do we lose from using this solution? there's always that, yes, it's good, but, yes, but what's it, but thing, right? So it's always important for you to understand this because your team needs to know what are the trade-offs, then you can make an informed decision on what are the options that you should choose. Highly scalable systems are also often very complex because you need to have things that are distributed, you have things that are loosely coupled, you have things that are like in a few places. So you need to do a lot of automation to make sure that things operate and deploy properly. For example, in my current application that my team works on, we have EKS instance and we have Docker containers we need to deploy. We also have Lambda function we need to deploy. We have the SQS queues we need to set up. And all this has to all work when we deploy shit. Otherwise, shit hits the fan, right? So basically, you need to know what are the complexities you're dealing with. So you want to move from scaling. Sometimes scaling problems, when you solve it, it will become an orchestration problem. Basically, how do I orchestrate the deployment of my containers, my EKS is set up? So there were instances where we deploy something, but then we forgot to set up the the permissions on the Lambda function. So the Lambda failed to deploy, and we're like, oh no, this is a critical Lambda function, and yeah, things like that can happen. So having automation, like using Terraform or some form of infra as code, is very helpful in helping you manage this complexity. Because there are many moving parts, you want to make sure they all work in tandem. The thirdly is team culture. So basically, your team has to be has an open learning and collaborative culture because you really want everyone to work together to come out with the best solution, right? So you have a situation where the team is refusing to learn, no matter how you try to, or refuse, not open at all to new ideas, no matter how much you try to convince them that this is a better solution, they may not budge, right? So you want to make sure your team, and maybe your tech leads, and maybe to encourage your team members to read up about this, try this out, So some ways that we kind of manage this is to do technical spikes. Hey, I have this idea to do this, introduce this workflow engine in my workplace. So I then convince my team to go with that, go try out this solution. One way is to come up with a POC, proof of concept. So there's a short little spike to kind of validate our these assumptions. We assume that this is the problem of our system. I'm going to try and build something that could try and solve this problem. I'm going to do a POC to kind of like inform the team what are pros and cons and what can we actually do with this new solution. So sometimes when you think about scaling systems, you want to do short and quick experiments to figure out whether that solution is suitable for your team. Because every system is very different, right? It depends on what you want to optimize for. You want to optimize for speed, you want to optimize for capacity or whatever. So yeah, so you want to make sure that your team has open to this. Also about failure tolerance. How tolerant is your team to failure? So it's like if things break, what's our first reaction of the team, right? Because when things don't scale, things break down, what should we do, right? So which is why your team culture is important to help you build up psychological safety and, for example, no blame culture. So basically, if something goes wrong in the system, it's everyone's problem. It's everyone's problem. Our team has to look at what's going on. Or you can also delegate it to, like, say, a production support duty roster, and so that we know that, okay, this person is supposed to be taking care of it today, looking out for production alerts and whatnot, right? And then if he cannot tahan already, the rest can come in and help, right? So in my team, we have a concept of a level 1 production support and level 2 production support. Level 1, basically, they are the first people to get called by our customers. And if they come to a situation they cannot fix the problem, or I think this problem needs a deep dive into the source code to figure out what's going on, they pass on to level 2, which is other folks in my team. Yeah. So understanding how this your team works, the dynamics in your team, helps you in adopting new things and scaling things up and down. Yeah. Okay. So yeah, that's all I have about this. I took about half an hour ish, right? So yeah, should be okay. Okay. Thank you. Any questions about system design or the stuff I talked about? It's quite a lot, but I recommend you watch the video. Everything I talk about is in the video except the last slide. Okay. All right. So going forward, we have three facilitators. One will be me, and we have Sharon at the back. Sharon, wave your hand, and Naomi. Right. So three of us will be
facilitating one team. So what we'll do next is you can break into we'll break into the different breakout sessions. There'll be one at the back there, another one over there, another one here. So the three case studies. First one is about building a highly scalable web application. The second case study is about building a data pipeline. And the third is how about building a notification system, right? So depending on which of these three kind of like you're interested in, please go to that section. So I'll just go, so basically for the next 45 minutes, we'll be doing that. We'll take a short break and then we'll do a share back about the different things. So the highly scalable web application is we're going to build a medical claim system where locked-in users can submit claims and needs to upload photos. And the business owner would like to verify the authenticity of the receipts. They want to split bills, split the multi-page, so a lot of things here. So we'll dive deeper. If you have a link to the slides, can also go straight to this one. We'll talk about it. So so for this one, we'll be in front. Case study one will be in front here. Second case study is on data pipeline, which is where Sharon is. So you can go to her. She used to work in a food delivery platform, so I think she probably knows this a bit well. Yeah. So case study 3 will be about the notification system. So basically, Naomi, which will be at the back over there. Okay. So yeah, you can pick one of the 3 and go straight to that table, and then we'll take about 45 minutes. We will think about the different ways and things that we can do, okay. If we need to scan the QR code, we do. Let me try and flip back. And this is the QR code for this this slide, and you can go check out that page. Okay. Okay. So case study 1 in front, 2 over there with Sharon, and 3 with Naomi. Then basically talk a bit about, we discuss about that components and go. Sorry, go.